Okay, good afternoon, everyone. Okay, so I'll go ahead and hopefully some of you will join. Okay, so today is our second last day, and our last meeting will be next Tuesday. Kindly try to join for the practice of the final exam. Okay, maybe the other thing I want to kindly remind you that if you get some time, check out for the course evaluation. I request that if you get some time, you do you check out and do the course evaluation, and I think the due date is 21st. Okay, so I'll go ahead and go over some selected questions, and if you're interested in me going over a particular question, please let me know. Okay, so first, so this time I chose questions like towards the end, because usually they are more tricky compared to the questions that come first. Okay, so in quiz 35, I chose question 16, and question 16, we are required to compute that integral. Now, let me remind you, please, once again, if we don't have limits, then that is an indefinite integral, and don't always forget the integration constant. Okay, so some point to note. Okay, don't forget the constant of integration, and if you forget that constant, especially if you keep forgetting it for so many questions, then they're gonna take away some points, especially for your free response question. Okay, so in question 16, we want to take that integral, and most of these questions we are going to use the substitution. So you should be very careful to see what you're trying to substitute and make sure that some things cancel. That's all we need to do. Okay, so in question 16, I want to compute that integral, and knowing the how the derivative of a natural logarithm looks like, I see that my u substitutions will let u be equal to the natural log of 3x, and when I differentiate this both sides, du is the same as 3, which is the derivative of 3x, then divide by what you've differentiated, which is 3x, but you're respecting x. So what I'm saying actually is that du is the same as 1 over x dx. Now substitute everything back to the question. And therefore we shall have integral of natural log to the power 4 of 3 of x. Remember, natural log to the power 4 of 3x is the same as natural log. So that's the same as natural log of 3x, then the whole of it to the power 4. That's how it should be written. So natural log of 3x, we said let that be equal to u. So that will be u to the power 4, then over x, then times dx, but this dx from this expression here, you can see that dx is the same as x times du. So times dx, which is x times du. And when I do that, this x can cancel. So what do I have? So finally, I have integral of u power 4 du, and when I integrate u power 4, I get u power 5 over 5. But remember, I don't have limits of integration, so I don't have to forget the constant of integration. Now, I use the u substitution, but I have to make sure that my final answer is back to the original variable, which in this case is x, and therefore my integral that I'm looking for, which is natural log power 4 of 3x over x, then the x is the same as u, but u is natural log of 3x, then the whole of it to the power 5, then over 5, then plus as a constant of integration. If you want to write it the same way it is written in the question, maybe I'll ramp off this. If you want to write it in the same way it is written in the question, then our final answer would be natural log to the power 5 of 3x, then times 1 over 5, then plus as a constant of integration. Okay. In question 15, same thing, we want to do that kind of integration. Okay, so in question 15, we have integral of sine to the 9x cosine x. So I let my u to be equal to sine of x, because I know that when I differentiate sine, I get a cosine, and therefore it will cancel this cosine here. Now, one may say, hey, but when I differentiate cosine, I get negative sine, so one sine can cancel. That's right, but only one sine can cancel, and therefore you will remain with a sine to the power 8. And that sine to the power 8, it is a function of x, but you've changed stuff to a variable u, so you won't be able to take that integration. So when you're doing a substitution, you're doing a substitution in such a way that we change variables from one variable completely to another variable. So I'm changing variables from variable x completely to variable u. Okay, so du is the same as cosine of x, then the x, substitute everything back. So I have integral of sine to the 9x, but remember I said sine x is u, so this is u to the 9, then times cosine of x, then times dx, but dx from this expression, I see that dx is the same as du over cosine x, so this is du over cosine x, and therefore this cosine x can cancel, and like I said, you see that when I do that, I'll have everything in variable u. So now I'm integrating with respect to u, and when I integrate this, I'll get u to the power 10 over 10, then plus c. But we know what u is. U is the same as sine x. So this is 1 over 10, then sine of 10 to the x, then plus c. Okay. Thank you, Rodriguez, for joining. Question 14. Same thing, you have to figure out what you want to substitute for. Okay, so in question 14, I know that whenever I integrate exponential to the power 2x, whichever answer I'll get, that exponential will be there. So it tells me that, hey, maybe it will cancel with that exponential there. So in question 14, same thing, 10 is a constant. I'll bring it out for now. So integral of e to the 2x, then cosec squared of e to the 2x, and then the x. So I'm saying I can let my substitution u to be e to the 2x, and when I do that, I differentiate both sides, so du will be the same as 2 e to the 2x, then x. I hope we remember how to differentiate e to the 2x. Substitute everything back, so we shall have 10 integral e to the 2x, then cosec squared u, because I said e to the 2x is the same as u, then times dx, but from this expression here, dx is the same as du over 2e to the 2x. Okay, so e to the 2x and e to the 2x cancel. This 2 here comes outside, so we have 10 over 2, and 10 over 2 gives me 5. So finally, I have 5 integral cosec squared u du, and when I integrate cosec squared, I get negative cotangent. So this is negative 5 cotangent of u, but this is an indefinite integral, so plus x. Change back to the variable x, so this is negative 5 cotangent u, but u is e to the 2x, and then plus the constant of integration. Okay. Question 10, same thing. You just have to know which one you're going to let, or how you're going to do your substitution. So I will let u to be equal to square root of x, but square root of x, let me write it as x to the power half. So when I differentiate both sides, my du will be 1/2, then x to the negative 1/2, then the x. I want to write that nicely, du is the same as 1 over 2 x to the power half. Then the x, I hope you remember that. And I can actually say du is the same as 1 over 2 square root of x then times dx. So wherever I have dx, when I multiply both sides by this guy, then the x is the same as 2 square root of x times du. So substitute everything back, so we shall have integral of 11 to the power square root of x, which I said let that be u. Now, this other square root of x is also u, but I can leave it since I know that it's gonna cancel with that guy there. Okay, then times dx, but my dx is the same as 2 square root of x then du. And then this square root of x and that square root of x will cancel. Now, if you want, you could have left this as u and this as u, but still that u and that u will cancel, so it doesn't matter. Okay, so this is the same as 2 is a constant square root of 11, integral of 11 to the power u du. And this is something we know how to integrate from our last class. Remember when we took the integral of a to the x dx. I hope we remember what we get. So when I take the integral of 11 to the power u, this is the same as 2 is out, and this integral is the same as 11 to the power u then over the natural log of 11, but this is an indefinite integral, so I have to add on the constant of integration. But my final answer can't be in variable u. I have to change back to variable x. So therefore, my final answer is 2 times 11 to the power square root of x, then over natural log of 11, then plus c. Please note that 2 and this 11 cannot multiply to make 22. Why? Because 11 has a power on top, so these two guys cannot multiply together. The multiplication in a case like this is only possible if this other guy also has a base of 11. So if this was 11, then those two guys can multiply by adding up the powers, but these two things can now not multiply. Okay, and those are the 4 questions I chose in quiz 35. Quiz 35 is a little easy compared to quiz 36. So unless you really have a specific question you want me to go over, yeah, but I think Rodriguez, it's you who requested that maybe usually I go over the last question, so that's what I did. I chose the last questions apart from I just skipped question 10 after the last 3. Okay, if not, I'm gonna go over some questions in quiz 36. And my first question in quiz 36 will be question 14. Okay, I just saw your message. Okay. Okay, so question 14. This is also an indefinite integral. And like I said in our last discussion, we can integrate these guys separately, or you can integrate them at a go. Yeah, but usually when you separate these integrals, then life becomes a little easy. Okay. So I'm gonna separate these integrals. So this is integral of 10 over x minus 2, then the x, okay, then minus, I'm gonna use black, so minus integral of 2 over x plus 10, then squared dx, then minus integral of 4 over x squared plus 100 dx. Now, of course, if you do these integrals, if you really practice enough and you do so many questions, you realize that some of these integrals are really, really easy. For example, an integral of 1 over x minus 2 dx, without going through the whole of it, I'll see that this is just natural log of x minus 2. But that comes with a lot of practice, of course. So for me, I'm going to go like from scratch, but I'm saying that when you do enough practice, you may not need to waste a lot of time going from scratch for all these guys here. Okay, so the first integral, so my first integral, I'm going to do them separately. So my first integral is this integral here in dark blue. So this is the same as 10 outside, then 1 over x minus 2 dx. Now, since I'm doing this from scratch, then I'm going to have let u be equal to x minus 2. So du is the same as dx, because when I differentiate x minus 2, I just get 1. So take back in that integral, so I have 10 integral 1 over u, then times dx, but dx is the same as du from this guy here. And I know what I get when I integrate 1 over u with respect to u. I just get natural log of u, but this is an indefinite integral, so I'll add on a constant, and in fact, let me say this is constant 1 maybe. Okay. Now, I want to mention that, so this is the same as 10, then natural log of u, but u is the same as x minus 2, then plus some constant of integration. Now, before I continue there, this is what I want to say, that whenever I have an integral of a certain function, and that function is a quotient, in other words, it's in fraction form, then if I can take the derivative of the denominator and I get what is in the numerator, then the answer for that integral is just natural log of the denominator. Once again, if I have a function which is a quotient, so which is in fraction form, if I can take the derivative, if I realize, so you look at it and you realize that when I take the derivative of the denominator, then I can get what is in the numerator, then the final answer for that integral is the natural log of the denominator. Okay, so this is what I'm saying. I'm saying that if I have integral of f of x over g of x, then dx, okay? And I see that the derivative of g of x is the same as f of x, right? Then this integral here is just the same as the natural log of g of x. That's all I'm saying. Okay, so if you take an example, just if I can get an example, just a random one. If I take the integral, right, of x squared, let me say x, right, then over, so let's say 4x, then over 2x squared dx, right? By looking at it, just I can say this is the natural log of 2x squared dx. That answer should be, plus a constant. So that answer should be correct. Why? Because when I take the derivative of this guy here, I see that I get 4x. But maybe that, so this answer is correct, but the other person can decide to reduce this guy by this. So I get 2 here, and this is 1x goes, so I have integral of 2 over x. So this is 2 natural log of x, something like that. Yeah, but all I'm saying is that when I realize that when I differentiate this, for example, when I differentiate x minus 2, I get 1, then the final answer for this integral should be natural log of the denominator, which is x minus 2, and that is what we are getting there. Okay. Okay, then my second integral in green, I have the integral of 2 is outside, 1 over x plus 10 squared, then dx. Okay, and my u, I'll let u to be x plus 10. So once again, du is the same as dA. When I substitute everything back, then I'll have 2 integral 1 over u squared, then times dx, but dx is the same as du. Remember, I can write this as 2 integral u to the power negative 2 du. When I integrate this, I'll get 2. When I integrate u to the power negative 2, I get u to the power negative 1 over negative 1, then plus c. I'll call maybe this constant c2, and this is the same as negative 2 over u, then plus c2, but u is the same as x plus 10, so my final answer is negative 2 over x plus 10, then plus some constant, which I'm calling C2, and that is my second integral. My third integral in blue is the same as 4 outside, then integral 1 over x squared plus 100, then the x. Now, of course, whenever I see that, I think of something like 1 over x squared plus 1, which I know this final answer, if I'm integrating this is the arctangent of x. So I know I should be getting an answer which is in a line of that, but I need to know, of course, like I said, with more practice by looking at it, I can tell what the final answer looks like, but we are interested in knowing how you arrive at that answer. Okay, so this is 4 integral 1 over, remember what I want to create is, in the denominator, I want to create something like x squared plus 1. Now, this might not be x squared, but this must be 1. That is what I want to create. Okay? So I want to make sure that instead of having x squared plus 100, I have something squared then plus 1. And the way I can create that is by, if I factor out 100, then you can see that inside I'll remain with x squared over 100. Let me make the bracket a little bigger. So into x squared over 100, then plus 1 dx. I hope you see that when I open up these brackets here, then this 100 will multiply with this. I go back to x squared, then 100 times 1, I go back to 100. So I haven't changed anything, okay? Now this 100 is a constant, so it can reduce with that to make 1 over 25. So 1 over 25 is a constant, so I can bring it out. Then integral 1 over, look, we have x squared over 100. If I have x squared over 100, I can write it as x over 10, then the whole of it squared, then plus 1, and then dx. So once again, it's what we are interested in is something like this, and you see that that is what we have. The only difference is that instead of x squared, we have x over 10 squared, okay? I hope that is fine. Now, so this is how the tan substitution works. So I let that guy that is squared, which in this case is x over 10, to be the same as tangent of u, okay? I can also say this is x is equal to 10 tangent of u. I'm multiplying 10 both sides. When I differentiate both sides, I'll have dx is equal to 10 secant squared du, then du. When I substitute back everything, I'll have 1 over 25, which is out. Then integral 1 over x plus 10 squared, that is the same as tangent squared u, then plus 1 times dx, but from this expression here, the x is the same as 10 secant squared u du, okay? Tangent squared plus 1, this guy here is the same as secant squared. I hope you remember that. So therefore, this, let me try to avoid to write another similar step. So this secant squared and this secant squared will cancel, okay? I hope you see that. So what I remain with is the same as 10. This 10 is a constant, so 10 over 25. Then integral of du, and this is 10 over 25 by 5, that is 2, and over 5. Then times u, then plus some constant of integration, which I'm gonna call constant 3, okay? So finally, I have my final answers 2 over 5, but what is u? If you're very careful from this expression here, u is arctangent of x over 10. So this is arctangent of x over 10, then plus some constant of integration. So those are our three different integrals. And finally, I want to say that now combine them. So if we combine these integrals, my final answer would be 10 natural log of x minus 2 plus C1, of course, then minus. Now, if you're very, very careful, this is a minus 2, but there is a minus in the question, right? So that becomes a plus. So plus 2 over x plus 10 plus C2, of course, then minus 2 over 5 arctangent of x over 10, then plus C3. So C1, a constant, plus a constant, plus a constant. I'll just get one other constant which I can call C. Okay. Okay, question 12. I chose question 12. Same thing, we just have to make an appropriate substitution. But in question 12, now we have a definite integral because we have the limits of integration. So if we have the limits of integration, by the way, I want to mention that whenever you have the limits of integration, your final answer, 1, cannot have the constant of integration, and 2, your final answer cannot have the variable that you're integrating in. So in this case, your final answer cannot have x, okay? So in other words, your final answer should just be a number, a constant, which is a number. That is if you have the limits of integration. So in question 12, I will let my u to be equal to a squared minus x squared, and the u will be the same as negative 2x dx. Substitute everything back, so I have integral of 4x times square root of u, then times dx, but dx is negative du over 2x from this expression here. Okay, so the two can cancel, and I get 2 here, and the x will also cancel. Now, you realize that I'm avoiding to write the limits here because 0 to a, those are limits of variable x, but I'm changing to u. So it is not correct that I still write 0 to a when I have variable u, okay? 0 to a are variables of x, so when I go to variable u, I expect different limits which are not 0 to a, okay? So this is the same as 2 is a constant, integral, in fact, negative 2 because we have a negative there, then u to the half du. So this is negative u times u to the power 3 over 2 if I integrate, then over 3 over 2, then plus some constant of integration. But that constant really, I know I have the limit, so I can avoid it for now. Okay, so this is the same as negative 4 over 3, then u to the power 3 over 2. Now, so this is where you have a choice. I have my answer in u. So whenever I have limits, I have a choice. If I don't have limits, then I have no choice. I have to change back to the variable x. But if I have limits, after reaching my final answer for u, I can decide to change these limits from limits of x to limits of u, and I take those limits, or I can change my final answer back to the variable x, and I use the limits that I have in the question. So my first option, I can change this answer from u to x. So this will be negative 4 over 3 times u, which is a squared minus x squared, then to the power 3 over 2. And then I'll take limits from 0 to a. And when I do that, I'll have negative 4 over 3 into substitute a where there is x. So I'll have a squared. Just for context, let me write that. So this is a squared minus a squared to the power 3 over 2. Then minus, substitute the lower limit, which is 0. So this will be a squared minus 0 squared. So a squared minus 0 squared, then to the power 3 over 2. Okay? A squared minus a squared, that is 0. The whole of that guy becomes 0. So we have negative 4 over 3 into 0 minus, so this guy is also 0. This guy becomes 0, so it goes away. So I have minus a squared, then to the power 3 over 2. Now, a squared to the power 3 over 2, I can multiply those two powers together and the 2 will go. So I'll just remain with a cubed. I hope you see that. So this guy here, is the same as negative a cubed, and when those two negatives multiply with each other, I'll have a positive 4 over 3 then times a cubed. Now that is when I chose to change my final answer back to the variable x. Okay, that is one choice you can make. In the future, you might find that the final answer you have in U is easier to work with compared to when you change back to the variable a. So you need to know how to change the limits. So alternatively, change limits. So we have limits of x which are 0 and a, and we want to find limits of u. And we use this guy where we change our variable. So when x is 0, substitute 0 where x is, which is here, we get u is equal to a squared. So this is a squared. And then when x is a, substitute a there, you get u is equal to 0. Okay, so now come back to your final answer. Instead of going back to variable x, just keep your answer the way it is in u. And now you're evaluating from a squared to 0, because this was the lower limit in x, its corresponding lower limit is a squared in u. This is the upper limit in x, its corresponding upper limit is 0 in u. So this will be a squared to 0. But if you want really, you can substitute the limits directly the way they are here, you get an answer. But if you really remember very well, you know that in integration, the lower limit should be smaller than the upper limit. And if a is a constant, clearly a squared is always going to be greater than 0. Okay, so you can flip the limits, but remember what happens when you flip the limits. You multiply by a negative, so another negative multiplies with this and we get a positive. So alternatively, you can substitute limits here, or you can say this is positive 4 over 3, then u to the power 3 over 2. But when I do that, my limits will be from 0 to a squared. If you do this and you do this, you should get the same, you should be ending up with the same answer. Okay, so this is 4 over 3. Let me use the second one. Into u to the, so we are substituting this guy where there is u. So that is a squared to the power 3 over 2, which is a cubed, then minus, when I substitute, I get a 0. So this is 4 over 3 times a cubed, which is exactly the same as that. If I use, just for completion, if I continue here, I'll have negative 4 over 3 into 0, I'll have 0, then minus a cubed. So you can say I have negative 4 over 3 into negative a cubed, and this negative and this multiply, and we go back to the same answer. So all the cases give you really the same answer, but my main point really is between the dark blue and the orange working. So the dark blue is where I have my final answer in variable u, and I have to change the whole answer back to the original variable. In orange, I have my final answer in variable u, and instead of changing back to the original variable, I rather change the limits from the limits of the original variable to the limits of the new variable, which is u. And so whichever you find easy is really what you do, but I'm saying that for some questions in future, you find that going back to the original variable gives you something. It may not be difficult, but it may be tedious to substitute those limits back. And you find that the easiest thing to do is maybe changing the limits like that. Okay. Question 13 is just a substitution, and we have, so I'll have u is equal to 7 plus sine squared x. So my du is the same as 2 sine of x, then cosine of x dx. I hope you remember how to differentiate sine squared of x. Substitute everything back, so we shall have integral of 4 sine of x cosine of x, then over square root of u, then times dx, but dx is the same as du over 2 sine of x cosine of x. So the sine of x cosine of x will cancel, and the 2 will also reduce this 4 by 2. So finally, I have 2 square root of 1 over u to the power half du, and this is 2 integral of u to the power negative half u. When I take this integral, I'll have 2 times u to the power half, then over 1 half, of course, plus some constant of integration, because we don't have limits there. And when I do this, this is 4u to the power half, then plus c, change back to the original variable. So this is 4u, but u is 7 plus sine squared x to the power half, then plus c. And this is the same as 4. I can write back in that, and I put a square root, so 7 plus sine squared x and a square root, then then plus c. Okay, and maybe that wasn't really so difficult. Uh, for me, finally, maybe I chose question 10. I don't know, maybe I think that it is a little tricky, but question 10 looks like something we've done concerning the arctangent. And really, I should remember that when I see 1 over x squared minus 1, this is arc sine. So I see something like that here, right? So I think it is, 1 over square root of 1 minus x squared. So that should be arc sine. So I see that this looks like that. So I want to modify this denominator such that instead of 81, I have a 1, then minus something squared. Okay? So this is the same as integral, or maybe the first thing I can do actually is, okay, it's fine. So this is the same as 6x plus 3, then over a square root of 81. If I pull out 81, then I'll have 81 into 1 minus x squared over 81, then dx. Please note that if I open this bracket here, then I'll go back to 81 minus x squared, which is the original guy there. But don't forget that in this case, we have a square root. Previously, concerning arctangent, we don't have that square root, so you should be careful. You should be careful with that, really. So this is the same as integral of 6x plus 3, then over, now, square root of xy, remember it is the same as square root of x, then times square root of y. So all I'm saying is that square root of this square root is the same as square root of 81, then times square root of this. Square root of 81 is the same as just 9. Okay, so this 81, when it moves out of the square root, it comes out as a 9. So this guy will be the same as 9, then times square root of 1 minus x over 9 squared, then the x. Okay, I hope that is fine. So now I can separate these integrals by distributing the denominator to both of these guys. So I'll have the first integral maybe in orange is the same as integral of 6x over 9 square root of 1 minus x squared, x over 9 squared, then dx. Okay, then plus the second integral, which is just integral of 3 over 9 square root of 1 minus x over 9 squared, then dx. Okay, so I'm going to first do the orange one. So when I do the orange one, 6 over 9 is a constant, so it can come out. Then integral of x over 1 minus x over 9 squared and the square root, then the x. Now I realize that when I differentiate this guy down now, I won't have x directly, but I'll have something that has x, and x can cancel. So therefore, this is just a substitution. So let u be 1 minus x squared over 81. So my du is the same as negative 2x over 81, then dx. Substitute everything back, we shall have 6 over 9 integral of x over square root of u, then times dx. But from this expression here, dx is the same as negative 81 over 2x, then du. So this x can cancel, 2 can cancel this by, and we remain with 3. This 9 can cancel this 81 to remain with the 9 right there. Okay. So this guy is the same as 9 times 3, that's 27, but there is a negative, so this is negative 27 integral of u to the power negative half du. Remember, this is 1 over square root of u. If I bring it on top, it will be u to the power negative half. Now, when I take this integral, I'll have negative 27 u to the power 1/2 over 1/2, then plus c, and maybe I'm going to call that constant of integration, let's say c1. So this is negative 54. Okay. Because this 2 will multiply up, 2 times 27, that's 54. Then u to the power half, then plus c1. If I go back to the variable x, u, remember u was the same as 1 minus, so square root of 1 minus x squared over 81, then plus c1. If you want to make it look so nice, really, this is negative 54 square root of 81 minus x squared, then over 81, I'm getting the LCM, then plus c1, and this is negative 54 times square root of 81 minus x squared over square root of 81, which is 9, then plus c1. Okay, then by 9, 1, by 9, 6. So my final answer, I just have negative 6 square root of 81 minus x squared, then plus c1. Remember, that is just the integral for the guy in orange. Okay, then the guy in yellow, that is the sign substitution, and I'm going to let x over 9 to be equal to sine of u. So my dx, let me put this 9 over the other side. So x is equal to 9 sine of u. So dx is the same as 9 cosine of u du. Substitute everything back. We have 3 over 9, which is actually 1 over 3. So 1 over 3 comes out, so we shall have 1 over 3 integral of 1 over 1 minus x over 9 squared, that is sine squared u, and the square root, then times 9 cosine of u du. I'm substituting for this dx here, which is right there, okay, which gives me this guy here. Now, 1 minus sine squared u and the square root. 1 minus sine squared u is the same as cosine squared u. Let me write that real quick here. So 1 minus sine squared u is the same as cos squared u. And cos squared u under the square root means that we just remain with cos u. And therefore, that cos u cancels with that cos u up there. So what I remain with is 1/3 integral. In fact, 9. There is a 9. Yeah, there is a 9. So by 3, 1, by 3, 3. So what I remain with is just 3 integral of du. And this is 3u plus c. Back to the variable x, this is 3. But u from this expression here, u is the same as arcsine. So this is arcsine of x over 9, then plus c. And finally, my final answer, remember we separated the integrals, so I add them again. So my final answer is -6 square root of 81 minus x squared plus c1. Let me call this guy c2. Then plus 3 arcsine of x over 9 plus c2. Once again, c1 plus c2, a constant plus a constant. I get another constant which I can just call c. Okay. Rodriguez, are you still there? Okay.
Yes.
Any questions, especially in quiz 36?
I think you went over the ones I had a question on.
Okay. And it is fine now?
Yes. Thank you so much.
Okay. Okay, I'm gonna stop here. Rodriguez, I started before you came, but on top here, I was trying to remind you, mostly it is you and some other guy, I think Alexander, who have been attending. So please, if you can get some time, you can go and do the course evaluation, okay?
Okay.
Okay. I hope to see you on Tuesday for the final practice.
Yes. I will be there.
Okay, bye.
Thank you so much. Have a good day. Bye.